Have you ever looked up at the night sky and felt a sense of wonder at the vastness spread out above you? Those countless points of light, the distant galaxies, the silent, majestic sweep of the cosmos. It feels like we're seeing everything there is to see. But what if that feeling is an illusion? What if the universe we observe is only a sliver of what's truly out there, and the real story is unfolding in a direction we can't even see? This isn't just science fiction, it's a serious possibility that some of the world's leading cosmologists are exploring right now. The idea that the universe might be growing in a hidden dimension challenges one of the most deeply held principles of modern science, that the cosmos is the same in every direction. If true, it would mean that our place in the universe isn't just humbling, it might be fundamentally limited, like living in a room with a window that only shows one wall of a much larger world. Think about that for a moment. Everything we think we know about the cosmos, from the Big Bang to dark energy, from the formation of galaxies to the fate of everything, could be based on an incomplete picture. What if the expansion of the universe isn't uniform, but instead has a preferred direction, a kind of cosmic current flowing in a dimension beyond our perception? This single idea opens up breathtaking possibilities. It could help explain some of the most stubborn mysteries in physics, like why measurements of the universe's expansion don't quite agree, or what dark energy really is. It might even reshape our understanding of reality itself, suggesting that the dimensions we experience are just part of a far richer and more complex cosmic fabric. In this video, we're going to embark on a journey into one of the most provocative and exciting frontiers of modern cosmology. We'll explore the scientific theories that allow for a universe growing in an unseen direction, from the mathematics of extra dimensions in string theory to the subtle clues hidden in the oldest light in the universe. We'll look at how astronomers are using cutting-edge technology to search for signs of this hidden growth, and we'll consider what it would mean for us, for our place in the cosmos, and for the future of everything. This is more than just a tour of abstract ideas. It's an invitation to rethink reality alongside the scientists who are daring to ask these profound questions. So join us as we venture beyond the visible, into the realms of the unknown, where every discovery reveals not just answers, but deeper, more fascinating mysteries waiting to be explored. To truly grasp just how revolutionary the idea of a universe growing in a hidden direction really is, we first need a solid foundation in our current, best understanding of the cosmos. This foundation is known as the Lambda-CDM model, often called the standard model of cosmology. At its heart are two incredibly powerful assumptions about the nature of the universe on its very largest scales. The first is homogeneity, which simply means the universe is roughly the same everywhere. No single spot is truly special or unique. The second is isotropy, meaning the universe looks the same in every direction we care to look. There's no preferred axis, no cosmic north or south. This concept that we do not occupy a special place in the universe is known as the cosmological principle, and it's the bedrock upon which modern cosmology is built. And for good reason. The evidence supporting this view is nothing short of overwhelming. Think about the cosmic microwave background radiation, that faint afterglow from the Big Bang that fills all of space. When we map it with incredible precision using satellites like Planck, we find it is almost perfectly smooth, with only tiny, random variations in temperature. No matter which way we point our telescopes, this ancient light tells the same story. Furthermore, massive galaxy surveys that map the positions of millions of galaxies reveal a vast cosmic web of filaments and voids that, when you zoom out far enough, appears statistically the same in every direction. This model, with its ingredients of dark energy lambda and cold dark matter CDM, has been spectacularly successful at explaining the universe's evolution from its earliest moments to the vast structures we see today. Yet, even this remarkably successful model is not without its cracks. Persistent anomalies are emerging that suggest our picture might be incomplete. The most famous of these is known as the Hubble tension. In essence, we have two primary ways to measure how fast the universe is expanding right now, a value known as the Hubble constant. One method uses the early universe, the cosmic microwave background, as a starting point and extrapolates forward using our model. The other method looks at the late universe, measuring the distances and speeds of nearby stars and supernovae. These are two completely independent roads that should lead to the same answer, but they don't. They disagree significantly, and despite years of checking and rechecking, this discrepancy refuses to go away. It's like having two incredibly precise clocks that stubbornly tick at different rates, and no one can figure out why. This tension, among other smaller curiosities, is a tantalizing hint that the lambda CDM model, for all its successes, might be missing a piece of the puzzle. It forces cosmologists to be intellectually courageous, to ask if one of our core assumptions could be wrong. What if the universe isn't perfectly isotropic? What if there is a subtle preferred direction after all? A direction that would affect how we measure expansion from different vantage points. This isn't about throwing out our hard-won knowledge, but about building upon it, about considering that the cosmic rulebook might have a chapter we haven't read yet. These puzzles are the very reason the radical idea of directional expansion is now being taken seriously, opening a door to a universe that is far more complex and fascinating than we ever imagined. So if our standard model of the universe, for all its successes, might be missing something, where could we possibly look for answers? One of the most profound and mathematically elegant places to search is in the realm of string theory. This framework, a leading candidate for an ultimate theory of everything, suggests a reality far stranger and more magnificent than our everyday experience. We are all intimately familiar with the three dimensions of space: length, width, and height that define the world around us, plus the one dimension of time. But string theory posits that for the math to work, for gravity and quantum mechanics to finally shake hands, the universe must actually have more dimensions. Not 4, but 10 or even 26, depending on the specific version of the theory. Now, a natural and immediate question arises. If there are all these extra dimensions, where are they? Why can't we see them or move through them? The prevailing answer for decades has been a process called compactification. Imagine a single, incredibly long garden hose stretching off into the distance. From a great distance, it looks like a simple one-dimensional line. But if you were an ant on that hose, you would discover a second dimension, the circular direction around its thin circumference. String theory suggests that the extra dimensions of our universe are like that circular direction, but curled up into a space so fantastically tiny, on the scale of the so-called Planck length, that they are completely invisible to us and our instruments. All the particles and forces we know are, in a sense, stuck on the three-dimensional surface of this higher dimensional reality, which physicists call a brane, short for membrane. But here is where the plot thickens and connects directly to our cosmic mystery. What if one of these extra dimensions isn't completely locked away? What if, at some point in the history of the cosmos, one of these tiny, curled-up dimensions began to unfurl and expand? This wouldn't be an expansion we could see or point to within our familiar three-dimensional space. Instead, it would be a growth happening in a direction fundamentally perpendicular to everything we know. From our limited perspective, it would be completely invisible, a hidden axis of cosmic evolution. Yet, its effects could be felt everywhere. This is where a seemingly abstract idea from theoretical physics crashes directly into one of the biggest observational puzzles in modern cosmology: dark energy. We see the universe's expansion accelerating, but we don't know what's causing it. If a previously compactified dimension began to expand, the energy and dynamics of that process could manifest in our three-dimensional world as a force that drives galaxies apart. In this scenario, what we call dark energy might not be a mysterious substance or a property of space itself, but rather a shadow, a projection into our world of a dramatic event happening in a dimension we cannot access. It would be a cosmic illusion, but one with very real and measurable consequences. This brilliant, if speculative, connection shows how the answers to our biggest questions might not lie in finding new particles within our dimensions, but in finally acknowledging the existence of dimensions beyond our own. But if the universe's hidden growth is written in the language of extra dimensions, where might we look for its signature? The answer lies in the oldest light we can see, the cosmic microwave background, or CMB. This faint glow is the cooled remnant of the Big Bang's fiery beginning, a snapshot of the universe when it was just 380,000 years old. For the most part, this ancient light is incredibly uniform, a near-perfect sea of microwaves bathing the entire cosmos. This smoothness is a cornerstone of the Standard Model, powerful evidence for a universe that started off largely the same everywhere. Yet, when we look with exquisitely sensitive instruments like the Planck satellite, we don't find perfect uniformity. We find a tapestry of incredibly subtle temperature variations, tiny fluctuations of a few millionths of a degree. These anisotropies, as they're called, are the seeds of all future structure, the slightly denser regions where gravity would eventually pull matter together to form galaxies, stars, and us. Most of these fluctuations are random, with no particular pattern or preference. But nestled within this data, some cosmologists believe they have found something deeply strange, something that hints at a fundamental break in the symmetry of the cosmos. The most famous and controversial of these anomalies has been dramatically nicknamed the axis of evil. This isn't a literal axis of doom, but a surprising statistical alignment in the CMB fluctuations. Essentially, some of the larger scale patterns in the temperature map seem to line up with each other and with the geometry of our solar system in a way that, according to our standard isotropic models, they really shouldn't. It's as if the universe has a faint, preferred direction imprinted on it from the very beginning. Other curious features persist, like a large, unexplained cold spot in one hemisphere or a puzzling asymmetry in the average temperature between one half of the sky and the other. Now, it is absolutely crucial to approach these findings with a heavy dose of scientific caution. The statistical significance of these anomalies is debated. They could very well be flukes in the data, subtle artifacts of how we process the measurements, or simply cosmic variance, the idea that even in a perfectly uniform universe, our particular local view might just look a little odd. The scientific community is far from a consensus on whether the axis of evil is a real physical phenomenon or just a compelling mirage. But their persistent presence in the data is precisely what makes them so scientifically valuable. They are the loose threads in the fabric of our cosmological model, and when you pull on them, they lead you to ask profound questions. What if these aren't just measurement errors? What if they are genuine clues? This is where the idea of directional expansion offers a potential explanation. If the early universe was not perfectly isotropic, if it had even a tiny preferred direction of growth, that initial asymmetry would have left its mark on the cosmic microwave background. The physics of the early plasma would be slightly different along that hidden axis. potentially creating just the kind of large-scale alignments and temperature asymmetries that we seem to detect. The axis of evil could then be a fossil, a relic from a time when the cosmos was first defining its geometry, pointing us toward the dimension we cannot see. It encourages us to take these anomalies seriously, not as problems to be explained away, but as potential signposts pointing toward a deeper, more complex reality. While the cosmic microwave background gives us a glimpse of the universe's infancy, the large-scale structure we see today is the result of billions of years of growth and evolution. And it is anything but a random, featureless soup. Thanks to massive mapping projects like the Sloan Digital Sky Survey, we now have a stunningly detailed picture of the cosmos on the grandest scales. It reveals a vast, intricate architecture often called the cosmic web, a magnificent network of dense galaxy clusters connected by long, thread-like filaments, all surrounding enormous, nearly empty regions known as cosmic voids. This web is the skeleton of the universe, and its form is shaped by the rules of gravity and the initial conditions set by the Big Bang. If the universe were expanding in a hidden direction, this grand cosmic architecture would be the canvas where its signature might be most clearly written. The force of this directional growth could act like a subtle cosmic wind, gently shepherding matter to flow along its invisible axis. Over eons, this preferential motion could leave a distinct imprint on the web. Instead of the roughly spherical voids and randomly oriented filaments we expect in a perfectly isotropic universe, we might find evidence of something more organized. Voids could become stretched and elongated, taking on a more elliptical shape aligned in a particular direction. The great filaments themselves, which are already the largest coherent structures in the universe, might show a surprising tendency to line up with one another, as if countless galactic pearls were all strung on the same invisible string stretching across the cosmos. This isn't just speculative thinking. Cosmologists are actively testing this idea using sophisticated computer simulations. They create virtual universes in supercomputers, some that follow the standard rules of isotropic expansion and others programmed with a slight directional preference. When they let these digital universes evolve over billions of simulated years, the differences become clear. The anisotropic simulations can produce large-scale structures with telltale signs of alignment patterns that are statistically distinct from the more chaotic, symmetrical web of the isotropic models. The key now is to take these theoretical predictions and compare them against our real-world observations. This is where projects like the Sloan Digital Sky Survey become absolutely crucial. By meticulously mapping the three-dimensional positions of millions of galaxies, these surveys provide us with the most accurate chart of the cosmic web we have ever had. Astronomers are now scouring this incredible dataset, using advanced statistical tools to search for any large-scale alignment of filaments or systematic elongation of voids that might betray a hidden directionality to cosmic expansion. While the evidence is not yet conclusive, some intriguing hints have emerged: subtle statistical tendencies for structures to align over truly staggering distances that are difficult to explain with our standard model alone. These potential anomalies are like faint cracks in an otherwise smooth surface, suggesting there might be more to the universe's geometry than we currently perceive. Now, let's turn our attention from the grand architecture of the cosmic web to the very motion of its constituent parts. Every galaxy and cluster in the universe is caught in a kind of cosmic dance, with two primary movements guiding its steps. The first is the Hubble flow, the overall expansion of the universe that carries galaxies apart from one another, like raisins in a rising loaf of bread. But superimposed on that smooth, uniform expansion are what astronomers call peculiar velocities. These are the individual, local motions of galaxies, caused by the relentless tug of gravity from nearby massive structures. A galaxy might be pulled slightly toward a neighboring cluster or pushed along a filament of the cosmic web, creating a unique velocity that deviates from the pure Hubble expansion. On relatively small scales, these peculiar velocities are expected and well understood. What has truly captivated and perplexed cosmologists, however, is the suggestion that on the very largest scales imaginable, spanning billions of light-years, these motions might not be random at all. Instead, some observations indicate that colossal volumes of space containing thousands of galaxies might all be drifting together in the same direction. This coordinated motion is known as bulk flow, and it's as if a vast section of the observable universe is slowly, steadily drifting like a great ship on a cosmic current. The sheer scale of such a motion is staggering, encompassing a volume of space so immense that, according to our standard model of cosmology, it simply shouldn't be possible. The gravitational pulls from known structures shouldn't be strong enough or coordinated enough to create such a massive, unified drift. The evidence for this phenomenon is among the most heated debates in modern cosmology. Some studies using the observed motions of galaxy clusters have reported detecting these enormous bulk flows, with the entire complex moving at speeds of hundreds of kilometers per second toward a specific patch of the sky near the constellations of Centaurus and Vela. Other teams using different methods or datasets find no such signal, arguing that the initial findings are statistical flukes or the result of subtle measurement biases. The question of whether bulk flows of this magnitude truly exist remains an open and contentious issue, but if they are real, the implications are profound because they point to a universe that is not in equilibrium. Such a colossal motion demands an equally colossal explanation. This is where our journey into anisotropy finds another compelling piece of the puzzle. A bulk flow on this scale could be the gravitational pull of a supermassive structure far beyond our current observational horizon, something so enormous it makes our local superclusters look like pebbles. But another, even more radical possibility is that this motion isn't caused by a pull from outside, but is instead a fundamental feature of the expansion itself. If the universe is growing in a hidden direction, it wouldn't just be stretching space, it could also be gently shepherding matter along that preferred axis. The coordinated motion we detect as bulk flow could be the visible echo of that invisible current, a drift not towards something but along something. The galaxies within this vast stream might be behaving like leaves caught in a river, all moving together because the water itself is flowing in one dominant direction. This perspective transforms bulk flow from a strange anomaly into a potential Rosetta Stone, a direct measurement of the universe's hidden geometry and a powerful way to test models of anisotropic expansion. And so we arrive at one of the greatest enigmas in all of modern science, dark energy. For decades, astronomers have known that the universe isn't just expanding, that expansion is actually speeding up. Galaxies are flying apart from each other at an ever-increasing rate, as if some mysterious, repulsive force is woven into the very fabric of space itself. We've given this force a name, dark energy, but its true nature remains utterly unknown. It's the dominant component of our universe, making up about 68% of all its energy and content, yet it is completely invisible and detectable only through its cosmic push. The leading theoretical candidate for dark energy is the cosmological constant, an idea even Einstein briefly entertained, which represents a constant energy density filling space homogeneously. But this idea comes with its own deep puzzles, primarily the infamous fine-tuning problem. The predicted value for the energy of the vacuum from quantum theory is astronomically, almost laughably, larger than what we observe, off by a factor of 10 to the power of 120. This is arguably the worst prediction in the history of physics, suggesting that our understanding of the vacuum energy is fundamentally flawed, or that some miraculous cancellation must be occurring. It's a problem so severe that it pushes cosmologists to consider radically different explanations. This is where the concept of a universe growing in a hidden direction offers a breathtakingly elegant alternative. What if the acceleration we measure isn't being driven by a mysterious new form of energy at all? Instead, imagine that the dynamics of expansion are simply more complex than we assumed. In an anisotropic model where a hidden dimension is itself expanding, this growth could project a force into our familiar three-dimensional world. From our limited perspective, confined to our three-dimensional slice of reality, this would look exactly like an accelerated expansion. The mathematics shows that if a higher dimension evolves in a certain way, it can perfectly mimic the effects of a cosmological constant, creating the illusion of dark energy without requiring any new, exotic substance or a perfectly fine-tuned vacuum energy. It would be a cosmic sleight of hand where the true cause of the acceleration is not a what but a where, a process happening in a direction we cannot point to. This perspective doesn't just swap one mystery for another, it potentially resolves a major philosophical hurdle. The standard model requires us to accept that an unimaginably precise and unlikely cancellation just happened to occur, leaving us with the tiny sliver of vacuum energy we observe. An anisotropic explanation, rooted in the geometry of extra dimensions, could naturally produce the observed acceleration without any need for such miraculous fine-tuning. The rate and effect would emerge from the underlying physics of the higher dimensional space. This shifts the question from why is dark energy so inexplicably weak to what is the dynamics of the higher dimensional cosmos. It's a reframing that many physicists find more satisfying as it connects two profound puzzles, the nature of dark energy and the existence of extra dimensions into a single cohesive picture. The acceleration of the universe may not be a clue about a new force, but the first faint signal from a dimension beyond our own, a message written in the motion of galaxies. For centuries, one of the most powerful and humbling ideas in science has been the Copernican principle, later refined into the cosmological principle. It tells us that we do not occupy a privileged or special place in the universe. The Earth is not the center of the solar system, the Sun is not the center of the galaxy, and our galaxy is just one among countless others in a vast, homogeneous cosmos that looks essentially the same in every direction. This principle of mediocrity is the bedrock of modern cosmology, the very assumption that allows us to believe that the laws of physics we discover here are the same everywhere. It's a democratic view of reality, and it has been spectacularly successful. But what if this foundational belief is wrong? The possibility that the universe is growing in a hidden direction delivers a profound challenge to this core tenet. If the cosmos has a preferred axis of expansion, then location and orientation suddenly matter in a way modern science has largely dismissed. A universe with a direction is a universe that is not the same everywhere. One region aligned with this hidden current might experience the flow of time or the fabric of space differently from a region oriented against it. This isn't just a minor adjustment to a model, it's a philosophical earthquake that forces us to reconsider our entire relationship with the cosmos. This immediately leads to some of the deepest questions we can ask. Would the fundamental constants of nature, those seemingly immutable numbers that dictate the strength of gravity, the speed of light, and the charge of an electron, remain constant along this hidden dimension? In our isotropic universe, we assume they are the same everywhere, a belief supported by observations of distant quasars and ancient gas clouds. But if the universe has a fundamental asymmetry, that assumption begins to look like just that, an assumption. The possibility of varying constants opens up a dizzying array of scenarios. What would a region of the universe look like where gravity is slightly stronger, or the fine structure constant is a fraction different? Such places might be utterly hostile to the atomic processes that make stars shine and planets form, let alone to the delicate chemistry of life as we know it. This transforms the cosmic landscape from a uniform arena into a potentially varied and hierarchical one. We might not be living in a random, average location, but in a very specific Goldilocks zone, not just in space but in orientation. Our three-dimensional slice of reality could be uniquely tuned, a placid backwater where the constants are just right for complexity to emerge, while other regions, tilted differently against the hidden axis, are barren wastelands governed by different, perhaps more hostile, physical laws. This idea resurrects a form of cosmic specialness, not of centrality, but of fortunate alignment. It suggests that the conditions for our existence might depend not only on where we are in the universe, but on how we are oriented within its full, higher dimensional geometry. This line of thinking pushes the investigation far beyond the realm of pure physics and into the domains of metaphysics and philosophy. It asks us to consider whether the laws of nature are truly universal laws or merely local bylaws, applicable only in our particular neighborhood of a much richer and more complex cosmos. The search for a directional universe is, therefore, more than a technical puzzle about expansion rates and cosmic backgrounds. It is a fundamental inquiry into the nature of reality itself, questioning the very uniformity we have always taken for granted and forcing a profound reconsideration of our place in the grand scheme of things. Of course, the most brilliant theoretical idea remains just that, an idea until we can find a way to put it to the test. We can't rewind the universe and run the experiment again with different settings. So how do cosmologists move from the tantalizing what if of a directional universe to concrete, testable science? The answer lies in one of the most powerful tools of modern research, the supercomputer. By building vast, intricate digital universes inside these machines, scientists can play out the consequences of anisotropic expansion over billions of virtual years, offering us a glimpse into what such a cosmos would actually look like. This process is far more complex than simply tweaking a few parameters. Creating a realistic simulated universe is a monumental task of physics and programming. Cosmologists start with the fundamental equations of general relativity, but instead of assuming the perfectly smooth, isotropic expansion of the Friedmann models, they use the more complex mathematical framework of Bianchi cosmologies. These models allow them to program in a specific type of anisotropy. Perhaps the universe expands faster along one axis, or maybe it has a slight rotational spin, or contains a property known as shear, where different directions not only expand at different rates but also distort shapes over time. They seed this digital space with the same initial conditions we believe started our own universe, a near-uniform soup of matter and radiation, imprinted with the tiny quantum fluctuations from the inflationary epoch. Then they set the simulation in motion. Trillions of particles representing dark matter and ordinary matter begin their gravitational dance under these altered rules of expansion. The computers calculate the complex interplay of forces, tracking how these particles clump together, how filaments of the cosmic web emerge, how galaxies form and collide, and how light propagates through this warped spacetime. They can run countless variations, each with a different strength or type of anisotropy, creating a whole library of possible universes that could exist if the underlying physics allowed for a preferred direction. The true power of this method isn't in the creating, but in the comparing. Once these simulated universes have fully evolved, researchers then ask a critical question: which one looks the most like our universe? They take the final output of the simulation, the detailed map of virtual galaxies, the pattern of the cosmic microwave background, the distribution of vast cosmic voids, and they compare it statistically to the incredible maps we've built from projects like the Planck satellite and the Sloan Digital Sky Survey. They aren't just looking for a perfect match, they're looking to see if introducing a bit of anisotropy solves persistent problems. Does it make the mysterious axis of evil in the CMB look more natural? Does it produce large-scale bulk flows that match the controversial observations? Does it create a cosmic web with faint alignments that resemble the hints we see in the real data? The results from these numerical experiments are already shaping the debate. Some simulations have shown that a small amount of anisotropy can indeed provide a better fit to certain large-scale structure observations than the strictly isotropic model. Others suggest that specific anisotropic models could potentially ease the Hubble tension, offering a way to reconcile the conflicting measurements of the universe's expansion rate by suggesting it's simply direction-dependent. This doesn't yet prove that our universe is anisotropic, but it powerfully demonstrates that the idea is not just wild speculation. It is a viable, testable alternative that can be rigorously constrained by data. These digital laboratories allow us to turn the philosophical wonder of a directional cosmos into a hard-nosed scientific investigation, narrowing down the infinite possibilities of what might be to a handful of what could realistically be. It's fascinating to realize that the very foundations for this radical rethinking of the cosmos were laid down almost a century ago, not as a fringe idea, but at the very heart of the physics revolution sparked by Albert Einstein. When Einstein applied his new theory of general relativity to the entire universe in 1917, he was actually trying to describe a static, eternal cosmos, which was the prevailing belief at the time. To make his equations produce this unchanging universe, he famously introduced the cosmological constant, a kind of repulsive energy to balance the attractive pull of gravity. Crucially, this first cosmological model was built on the assumption of isotropy and homogeneity. It was a universe that was the same everywhere and in every direction, a perfectly smooth and symmetrical entity. This assumption of a uniform cosmos became so deeply embedded in scientific thought that it was soon elevated to a principle. But almost immediately, other brilliant minds began to explore what happened if you relaxed that assumption. In the 1920s, Alexander Friedmann found solutions to Einstein's equations that described a dynamic, expanding universe, the very foundation of our modern Big Bang theory. And then, in 1949, the legendary mathematician and logician Kurt Gödel, a close friend of Einstein's at the Institute for Advanced Study, presented a solution that was truly shocking. Gödel's universe was rotating. It had a preferred axis of rotation, meaning it was fundamentally anisotropic. In this spinning cosmos, the fabric of spacetime was dragged around, and this rotation opened up the bizarre possibility of time travel into the past, violating our everyday notion of causality. While Einstein was deeply unsettled by these implications, he couldn't find a flaw in the math. Gödel had proven unequivocally that Einstein's own equations allowed for universes that were not the same in every direction. Throughout the mid-20th century, other physicists explored these anisotropic solutions, developing a whole classification system known as Bianchi cosmologies, which describe universes with different types of expansion and rotation along preferred axes. For a while, these were serious contenders for describing our reality. However, the discovery of the cosmic microwave background radiation in 1965 changed everything. The stunning smoothness and uniformity of that ancient light seemed to be the final, definitive proof that the universe was isotropic. The anisotropic models, with their spinning and shearing, appeared to be beautiful mathematical curiosities that simply didn't match the observed data. They were gently set aside, and the perfectly smooth Friedman models became the standard, unchallenged bedrock of cosmology for decades. Science, however, has a way of circling back. Old ideas are rarely ever truly discarded. They just wait patiently for new data to give them fresh relevance. Today, we are living in that moment of revival. Those subtle anomalies we've been discussing, the axis of evil in the CMB, the potential bulk flows, the stubborn Hubble tension, are the new data that is breathing life back into these once-forgotten theories. The anisotropic cosmologies of Gödel and others are no longer seen as mere mathematical exercises. They are being re-examined as potential frameworks that might explain the lingering puzzles that the standard model can't quite resolve. This is how science truly progresses, not by a straight march forward, but by a constant process of re-examination, where even the most settled assumptions are held up to the light of new evidence. The history of anisotropic universes is a powerful reminder that sometimes, to see the future of cosmology, we must first look back to its past. This journey into the geometry of the cosmos leads us back to the very beginning, to a fraction of a second after the Big Bang, where the most influential event in the history of the universe is thought to have occurred: cosmic inflation. The theory proposes that our nascent universe underwent a breathtakingly violent growth spurt, expanding by an unimaginable factor in an almost infinitesimally short time. This explosive stretching ironed out any primordial wrinkles, smoothing the cosmos into the remarkably uniform state we see reflected in the cosmic microwave background, and simultaneously magnifying tiny quantum jitters into the density fluctuations that would one day become galaxies. Inflation is a cornerstone of modern cosmology because it so elegantly explains why the universe looks so similar in every direction we look. It is the ultimate homogenizer. Yet, what if this great cosmic smoother itself was not perfectly smooth? What if the engine of inflation had a subtle bias, a tiny preference for one direction over others? This is the provocative idea behind anisotropic inflation models. In these scenarios, the inflattened field, the mysterious energy driver of this exponential expansion, might not have been perfectly uniform. Perhaps due to its own quantum origins or its interaction with other fields, it could have possessed a slight directional dependence. Think of it like stretching a piece of dough. If you pull evenly in all directions, you get a nice, round, flat sheet. But if you pull just a little bit harder in one direction, the dough becomes subtly elongated, retaining a memory of that preferential pull even after it's been stretched to an enormous size. In the context of the infant universe, that pull would have been imprinted on the fabric of space-time itself. The quantum fluctuations that were blown up to cosmic size would not have been entirely random. Their distribution would have carried a faint signature of that initial directional preference. Some regions of space aligned with this hidden axis might have inflated just a tiny bit more or less than others. This means the seeds of today's largest structures, the great walls of galaxies and the vast cosmic voids, might have been sown with a built-in orientation, a whisper of directionality encoded at the dawn of time. The potential axis of evil we might see in the CMB and the aligned filaments in the cosmic web could therefore be cosmic fossils, relics of an inflationary epoch that was not perfectly symmetric, but had just a hint of a favorite direction. Connecting this primordial asymmetry to the idea of a universe growing in a hidden dimension creates a profoundly elegant narrative. The directional preference set during inflation wouldn't be a random accident. it could be directly tied to the dynamics of a higher dimensional space. Perhaps the inflattened field itself was a higher dimensional entity, and its interaction with a dimension that was beginning to unfurl and expand caused the inflationary burst to be slightly anisotropic from the very first moment. In this view, the directional growth we've been exploring isn't a new phenomenon. It's simply the continuation of a process that started during the universe's first fleeting instants. The seeds of today's potential cosmic anisotropy were not just planted at the dawn of time, they were the very seeds from which time, space, and all structure emerged. This possibility forces us to ask a fundamental question: is the symmetry of our universe a perfect, intrinsic law, or is it merely an extremely good approximation, a nearly, but not quite perfect facade that hides a deeper, more complex underlying reality? This persistent discrepancy in measuring the universe's expansion rate, known as the Hubble constant tension, is far more than a simple statistical error to be ironed out with better data. It represents a genuine crisis in cosmology, a stubborn rift between two of our most trusted methods for understanding the cosmos. On one side, we have the pristine view of the early universe provided by the Planck satellite's map of the cosmic microwave background. By meticulously analyzing the patterns in this ancient light, cosmologists can extrapolate forward through 13.8 billion years of cosmic evolution, using the well-established lambda CDM model to predict what the expansion rate should be today. This method gives us a value of approximately 67 kilometers per second per megaparsec. On the other side, we have painstaking observations of the local, contemporary universe. Astronomers use a cosmic distance ladder built with Cepheid variable stars and Type Ia supernova as standard candles to directly measure how fast galaxies are moving away from us right now. This meticulous approach consistently yields a higher value, around 73 kilometers per second per megaparsec. The difference might seem small, but the precision of these measurements makes the gap statistically enormous and impossible to ignore. It's as if you calculated the exact age of a tree by counting its rings from the sapling stage forward, and then got a completely different number by measuring the circumference of its fully grown trunk. The two stories don't match, and it strongly suggests that our model of the tree's growth is missing a crucial piece of information. This is where the concept of a directionally growing universe transforms from a fascinating speculation into a potential game changer. Our entire standard model assumes that the Hubble constant is just that, a constant, the same in every direction for every observer at this moment in cosmic history. But what if that fundamental assumption is the very source of our problem? An anisotropic model shatters this uniformity, proposing that the expansion rate could actually depend on which way you look. In such a cosmos, the Hubble constant isn't a single number. It's more like a dial that changes depending on your orientation in space. The force driving the expansion could be stronger along one hidden axis and weaker along another, meaning that galaxies being carried along by that current would recede at different rates depending on their alignment with this fundamental directionality. This elegant idea offers a compelling path to resolving the tension. The measurements from the early universe, like the CMB, provide a kind of all-sky average. They capture the state of the entire infant cosmos, smoothing over any potential directional differences into a single, uniform value. However, the local measurements from supernova are taken from our specific vantage point within the cosmic web. If our galactic neighborhood happens to be oriented in a particular way relative to the universe's hidden expansion axis, we would measure a locally higher or lower expansion rate than the cosmic average. The discrepancy isn't an error, it's a real feature of the cosmos, a direct consequence of our location within an anisotropic universe. The Hubble tension, therefore, stops being an annoying puzzle and becomes a potential Rosetta Stone. It could be the first clear, quantitative evidence that the expansion of the universe has a preferred direction, a profound clue that we are not just measuring the growth of space, but our own orientation within a higher dimensional reality. This single observational dilemma might be the key that unlocks the door to a deeper understanding of physics, pointing us toward the hidden dimensions and forces that shape the cosmos. But if the very fabric of space is stretched differently along a hidden axis, the journey of light through that warped cosmos would be fundamentally changed. Light, the ultimate cosmic messenger, travels along the contours of spacetime itself. In a universe with a preferred direction of growth, those contours would be subtly deformed, like a vast, invisible landscape with gentle hills and valleys aligned along a specific compass point. This means that a beam of light traveling with the grain of this cosmic expansion might behave differently than a beam traveling directly against it. The most sacred constant in all of physics, the speed of light in a vacuum, is the bedrock of Einstein's theory of relativity. But in an anisotropic universe, this constancy could be an illusion limited to our three-dimensional perspective. From a higher dimensional viewpoint, the speed of light might actually vary depending on its orientation relative to the hidden axis, a concept that would require a monumental rewrite of modern physics. The consequences of this would ripple through every single one of our astronomical observations. The redshift of light from distant galaxies, our primary tool for measuring the expansion of the universe, would become ambiguous. A galaxy's redshift is currently interpreted as a pure measure of its velocity away from us, due to the stretching of space. But if space itself stretches light differently depending on its direction of travel, a galaxy's measured redshift would be a confusing mix of its true velocity and this directional bias. A galaxy positioned along the preferential expansion axis might appear to be receding much faster than it truly is, while a galaxy perpendicular to that axis might seem strangely sluggish. Our entire cosmic distance ladder, the carefully calibrated sequence of measurements that allows us to map the universe, would be thrown into question. Distances calculated from the brightness of standard candles like Type Ia supernova could be systematically over- or underestimated in different parts of the sky, creating a distorted and warped map of the cosmos that doesn't reflect its true structure. The Hubble tension itself, that stubborn discrepancy in expansion rates, could simply be the most obvious symptom of this universal directional bias in our measurements. Thankfully, astronomers are not powerless against this potential cosmic illusion. We now have the tools to go looking for these telltale signs of directional light travel. The key is to observe the same type of event or the same class of object from many different directions across the sky and see if their properties change in a systematic way. Distant supernovae, for instance, could be catalogued not just by their distance and redshift, but also by their precise celestial coordinates. If their apparent peak brightness or the stretch of their light curves shows a curious pattern, perhaps they are consistently dimmer or evolve faster in one hemisphere of the sky compared to the other. It could be a smoking gun for anisotropic light propagation. Similarly, the afterglows of incredibly powerful gamma-ray bursts, which can be seen from the farthest reaches of the universe, could be analyzed for directional dependencies in their properties. Perhaps the most exciting new probe is gravitational waves. These ripples in space-time, caused by cataclysmic events like colliding black holes, travel across the universe virtually unimpeded. If the speed of these waves depends on their direction, it would leave a clear signature in the data collected by observatories like LIGO and Virgo. By comparing the arrival times of gravitational waves with the flashes of light from associated gamma-ray bursts, scientists could search for a delay that changes depending on where in the sky the event occurred. Finding any such directional signal would be more than just a new discovery. It would be a revolution. It would mean that the stage upon which the universe plays out its drama is not the flat, uniform space we've always assumed, but a textured, oriented reality with a hidden geometry, challenging the very core of our understanding of spacetime and light. But to truly understand how this invisible scaffolding of the cosmos might be shaped by a hidden direction, we need to turn our attention to another great cosmic mystery: dark matter. This enigmatic substance makes up roughly 27% of the universe, a dominant presence that outweighs all the ordinary atoms in stars, planets, and us by a factor of about 5 to 1. We cannot see it because it does not emit, absorb, or reflect light. Its entire existence is inferred through its powerful gravitational influence. We see its pull on the orbits of stars within galaxies. We watch it bend the path of light from distant objects in a phenomenon called gravitational lensing, and we know it forms the massive gravitational wells around which the entire cosmic web is woven. Dark matter is the unseen architect of the universe's large-scale structure. Now, if the universe possesses a fundamental anisotropy, a subtle preference for expansion along a hidden axis, this cosmic current would not simply ignore the dominant form of matter in the cosmos. Just as it would shepherd visible galaxies and shape cosmic voids, this directional flow would also exert a profound influence on the distribution and behavior of dark matter. The gravitational pull that governs dark matter would itself be shaped by the underlying geometry of spacetime. In an isotropic universe, we expect the vast halos of dark matter that surround galaxies to be roughly spherical. They form through a process of gravitational collapse and interactions that, on average, should have no preferred direction. But in a universe with a directional expansion, that symmetry would be broken. The relentless, gentle push of expansion along a hidden axis would act over billions of years, subtly sculpting these dark matter halos. Instead of being spheres, they might become stretched, taking on a more ellipsoidal or even football-like shape, with their long axes systematically aligned with the direction of the universe's hidden growth. This wouldn't just affect individual galaxies, it would imprint itself on the largest scales of all. The great filaments of the cosmic web, which are predominantly made of dark matter, might show a surprising tendency to line up. The gravitational collapse that forms these structures could be influenced by the anisotropic expansion, causing matter to flow more easily along the preferred direction, reinforcing the alignment of these massive tendrils across the cosmos. The distribution of the most massive galaxy clusters which sit at the intersections of these filaments might also betray a pattern, appearing more frequently along a particular celestial alignment. This creates a powerful and testable prediction. If the universe has a hidden direction, then the invisible dark matter skeleton that holds it all together should bear the unmistakable marks of that orientation. Fortunately, we have a remarkable tool for tracing this invisible architecture: gravitational lensing. This effect, a stunning confirmation of Einstein's general relativity, occurs when the gravity of a massive object, like a cluster of galaxies rich in dark matter, warps the fabric of spacetime around it. This warping acts like a lens, bending and distorting the light from even more distant galaxies lying behind it. By meticulously analyzing these distorted images, stretching them from faint arcs into their true shapes, astronomers can create a detailed map of the mass responsible for the lensing, effectively making a map of the dark matter itself. This technique has already revealed the detailed structure of dark matter halos and filaments in stunning detail. The next step is to take these exquisite dark matter maps and search them for the subtle signs of anisotropy. Astronomers would analyze the shapes of thousands of dark matter halos, statistically checking to see if they are randomly oriented or if they show a faint but consistent preference to point in the same general direction. They would examine the vast cosmic web traced by dark matter, using complex algorithms to determine if the filaments show any large-scale alignment that defies the predictions of an isotropic universe. Projects like the European Space Agency's Euclid spacecraft and the Vera-C, Rubin Observatory's legacy survey of space and time are designed to perform exactly this kind of science on an unprecedented scale, mapping the dark universe with finer detail than ever before. A confirmed detection of a preferred alignment in the dark matter distribution would be monumental. It would connect two of cosmology's greatest mysteries, dark matter and the nature of cosmic expansion, suggesting that the invisibility of dark matter is somehow cosmically linked to the invisibility of the direction in which our universe is growing. This journey into the fundamental nature of reality brings us to the very edge of our understanding, where the smooth, continuous fabric of space-time itself begins to dissolve into something far stranger. For over a century, general relativity has given us a magnificent description of the cosmos as a dynamic stage, a four-dimensional continuum that can bend, warp, and expand. But we know this beautiful picture is incomplete because it completely ignores the wild, probabilistic rules of the quantum world that govern the very small. Uniting these two pillars of physics into a single theory of quantum gravity is perhaps the greatest unsolved problem in all of science, and it is here, at this frontier, that we might find the ultimate origin of a directional universe. The central idea emerging from several leading approaches is that space-time is not fundamental. The smooth, mathematical continuum we use in Einstein's equations may be an approximation, an illusion that emerges from a more basic, underlying reality, much like the smooth surface of a lake emerges from the chaotic dance of countless water molecules. Theories like loop quantum gravity and causal set theory propose that this deeper reality is discrete and granular. In loop quantum gravity, spacetime is woven from a network of tiny, one-dimensional loops, a spin foam of finite quanta of area and volume. In causal set theory, the universe is fundamentally a vast collection of discrete events, with only their causal relationships, which events can influence others, defining the structure of spacetime. In both cases, the continuum is a large-scale illusion. Now, if the bedrock of reality is a discrete structure, a natural question arises: is this structure perfectly symmetrical? Just as a crystal can have a preferred alignment of its atoms that gives it unique properties, the fundamental quantum grains of spacetime could possess an inherent anisotropy. Their connections might not be perfectly even in all directions. There could be a subtle preference, a microscopic grain or alignment woven into the very first moments of the universe's existence. As the universe expanded and cooled, this tiny quantum seed of directionality would have been stretched to cosmological proportions. The large-scale preference for expansion we've been exploring wouldn't be something that happened to the universe. It would be an echo of what the universe is at its most fundamental level. The hidden axis would not be a direction in space, but a direction of space, a fossilized memory of the anisotropic structure from which spacetime itself crystallized. This perspective is nothing short of revolutionary. It suggests that the search for a directional universe is not merely about fixing a cosmological model or explaining an anomaly. It is a direct probe into the quantum nature of gravity and the origin of spacetime. If the primordial anisotropy we infer from the CMB, or large-scale structure, can be definitively linked to a prediction from a theory of quantum gravity, it would provide our first experimental handle on physics at the Planck scale. We would be using the entire cosmos as a microscope to peer into the fundamental grain of reality. understanding how directionality emerges from the quantum foam could be the key that finally unlocks a complete theory of quantum gravity, blending the cosmic and the quantum into a single, profound narrative about the nature of existence itself. In our standard cosmic story, the fate of everything is a tragically uniform descent into cold, dark emptiness. Driven by the relentless push of dark energy, the expansion of the universe accelerates forever, eventually pulling all galaxies so far apart that the sky goes black, star formation ceases, and matter itself may decay, leaving behind a vast, frigid, and lifeless void in a scenario cosmologists call heat death. It is a singular, bleak, and isotropic destiny. The same chilling outcome awaits every corner of the cosmos, regardless of direction. But if the foundation of this story is wrong, if the universe is not expanding uniformly, but is instead stretching with a preference along a hidden axis, then this forecast for the end of everything must be completely rewritten. The future becomes not a single, predictable path, but a spectrum of possibilities shaped by geometry where direction determines destiny. Imagine a universe that is not simply growing larger, but is actively changing its shape over trillion-year timescales. If one dimension is expanding significantly faster than the others, the cosmos would evolve into an increasingly elongated and distorted version of itself. This isn't just a visual change, it would fundamentally alter the forces that govern the universe's evolution. Gravity, which works to pull matter together into galaxies, stars, and planets, would find its influence challenged in new ways. Along the axis of rapid expansion, the stretching of space would act like a powerful counterforce, making it increasingly difficult for gravity to gather matter together. Galactic clusters might be slowly pulled apart along this dimension, their constituent galaxies stretched into long, thin streams separated by unimaginable gulfs of nothingness. Meanwhile, in the directions perpendicular to this expansion, gravity could maintain more of its hold, potentially allowing structures to remain bound together for far longer, creating a bizarre cosmic geography of dense pancake-like regions separated by ever-widening abysses along the preferred axis. This reshaping of the gravitational landscape has direct and profound consequences for the most extreme objects in the universe, black holes. In our standard model, even black holes are not immortal. Through the slow quantum process of Hawking radiation, they are predicted to evaporate over astronomical timescales, but in an anisotropic future, their evolution could be stranger still. The different expansion rates along different axes could affect the space around a black hole, potentially altering its evaporation rate or even its stability. Some theoretical models suggest that in a highly elongated universe, black holes could become stretched into exotic objects like black strings or could merge in new ways, leading to a final era dominated by the dynamics of these distorted gravitational monsters. The very fabric of spacetime near them could be warped by the background anisotropy, creating environments that are simply impossible in a uniform cosmos. Perhaps the most dramatic departure from the standard model involves avoiding one of its most violent proposed endings, the Big Rip. In this scenario, dark energy becomes so dominant that it overwhelms all forces, first tearing apart galactic clusters, then galaxies, solar systems, planets, and finally the very atoms that make up matter itself in a catastrophic finale. However, several anisotropic cosmological models offer a potential escape clause from this apocalyptic fate. If the dark energy-like effect is not a uniform property of space, but is instead the result of expansion along a specific dimension, its influence could be channeled. It might not strengthen indefinitely to rip everything apart, but could instead reach a kind of equilibrium or evolve in a way that only stretches the large-scale structure of the universe without destroying bound systems like individual galaxies or stars. The end would not be a sudden, violent tear, but a more gradual and structured dissolution, a slow unraveling along a preferred cosmic thread rather than a simultaneous shredding of all reality. This completely reshapes our vision of cosmic destiny. The far future is no longer a uniform, cold, and empty wasteland everywhere. It becomes a patchwork of different environments. There could be regions oriented favorably relative to the hidden axis, where matter remains gravitationally bound for much longer, where the last stars flicker out eons later than elsewhere, and where the final embers of complexity and perhaps even life could cling to existence in isolated pockets long after the rest of the cosmos has faded into darkness and stillness. The end of the universe might not be a single event, but a drawn-out process that plays out differently in different directions, a final testament to a fundamental asymmetry written into the laws of physics themselves. This vision of a structured geometric end is not just a different answer, it's a different kind of answer, one that replaces a singular fate with a tapestry of outcomes woven from the hidden direction of cosmic growth. This idea that our universe might have a unique, hidden direction of growth leads us to an even more expansive thought. What if this isn't a universal rule, but merely a local feature? To explore that, we must step outside our own cosmic bubble and into the staggering realm of multiverse theories. The concept of a multiverse suggests that our entire observable universe, with its hundreds of billions of galaxies, might be just one isolated region within a much vaster and more ancient meta-reality. In scenarios like eternal inflation or the string theory landscape, new universes are constantly bubbling into existence, each with its own unique set of physical laws, constants, and perhaps even a different number of spatial dimensions. In this grand cosmic ecosystem, universes aren't stamped out on a production line to be identical. They are more like snowflakes, each one forming with a slightly different, random configuration. This framework provides a breathtakingly elegant context for the idea of a directional universe. The anisotropy we might be detecting, the potential preferred axis of expansion, would not be a fundamental law of all reality. Instead, it would be a quirky accident of our particular birth. In the infinite diversity of the multiverse, some universes might be perfectly isotropic, expanding with beautiful symmetry in all directions. Others might be wildly anisotropic, perhaps expanding rapidly in 2 dimensions while the third contracts. Our own cosmos could simply be one where the dice rolled for a mild, subtle directionality, a universe that is almost but not quite the same in every direction. This perspective doesn't diminish the finding, it magnifies it. It transforms a cosmic anomaly from a problem to be solved into a clue about our origins, a unique fingerprint that tells us which particular bubble in the multiversal foam we happen to inhabit. This connects directly to some of the most ambitious theories in physics, particularly the string theory landscape. This theory proposes a vast array of possible stable universes, each corresponding to a different way for the extra dimensions to be compactified. The specific way our 6 extra dimensions are curled up determines the laws of physics we experience, the strength of gravity, the mass of the electron, everything. But what if that compactification wasn't perfectly stable or uniform? A slight instability in one of those hidden dimensions could cause it to begin uncurling and expanding, creating the very directional growth we've been exploring. In this view, our universe's anisotropy is a direct consequence of its specific address in the string theory landscape, a local environmental feature that sets us apart from our myriad cosmic neighbors. This places the search for a preferred direction within a much grander quest, not just to understand our universe, but to understand the rules of the meta-universe that gave it birth, and to finally comprehend our place in a reality of literally infinite possibilities. While the theoretical possibilities are captivating, the true test of any scientific idea lies in its ability to make predictions that can be verified or refuted by observation. The next decade promises to be a golden age for cosmology, as a new generation of powerful telescopes and observatories comes online, each designed to map the cosmos with a precision we've only dreamed of. These aren't just incremental upgrades, they are revolutionary instruments that will peer deeper into space and further back in time than ever before, collecting data of such immense quantity and quality that they could finally settle the debate over a directional universe. Leading this charge is the James Webb Space Telescope, already astounding us with its detailed views of the early universe. While its breathtaking images of distant galaxies capture the public's imagination, its profound contribution to this specific mystery will be in charting the epoch of reionization, the period when the first stars and galaxies lit up and began to clear the cosmic fog. By mapping the distribution and orientation of these very first structures, Webb can search for any primordial alignment, any hint that galaxy formation itself was biased along a particular axis from the very beginning. It will provide a crucial, high-resolution snapshot of the infant cosmos, allowing us to see if the seeds of anisotropy were planted at the dawn of time. But to understand the universe's growth, we need to see its full, three-dimensional structure. This is the primary mission of the Euclid spacecraft, launched by the European Space Agency. Euclid is a dark universe detective designed to create the largest and most accurate 3D map of the cosmos ever made. It will observe billions of galaxies across more than a third of the sky, measuring their shapes and positions with exquisite detail. This immense catalog will be a treasure trove for cosmologists searching for the subtle fingerprints of anisotropy. They will use it to perform a cosmic geometry check, analyzing the shapes of galaxy clusters and the orientations of filaments within the cosmic web. Euclid's powerful eye will be able to detect even the faintest statistical preference for alignment, a whisper of directionality that would be drowned out in smaller, noisier datasets. It will also use weak gravitational lensing to map the invisible dark matter distribution, looking for any systematic stretching of halos that could betray the influence of a hidden expansion axis. On the ground, the Square Kilometre Array Radio Telescope project will add another crucial layer of data. By detecting the faint radio emission from neutral hydrogen gas in countless galaxies, the SKA will trace the cosmic web in a completely different way, allowing for independent verification of any large-scale patterns discovered by optical telescopes like Euclid. Its ability to see through cosmic dust and peer into distant epochs will provide a clean, clear view of the universe's structure, making it an invaluable tool for confirming or ruling out the existence of a preferred direction. Perhaps the most exotic and promising probes come from the burgeoning field of gravitational wave astronomy, as observatories like LIGO, Virgo, and the future space-based LISA detector listen to the ripples in spacetime from colliding black holes and neutron stars. They can perform a unique test. If the fabric of spacetime has an inherent grain or directionality, the speed of these gravitational waves could depend on their direction of travel. By comparing the arrival times of waves from events occurring in different parts of the sky, scientists could search for this telltale sign of anisotropy. Furthermore, the polarization of these waves, the way they stretch and squeeze spacetime, could also be rotated or altered if they propagate through an anisotropic universe, providing another independent line of evidence. The convergence of data from all these missions creates a powerful synergy. A hint of alignment from Euclid's galaxy map could be cross-checked against the dark matter distribution it also maps. A potential directional signal in the speed of gravitational waves could be compared to the orientation of cosmic voids found by the SKA. This multi-messenger, multi-wavelength approach is key to turning a curious statistical fluctuation into a confirmed discovery. The next decade will not be about waiting for a single silver bullet, but about weaving together countless threads of evidence from across the entire spectrum of astronomy. The goal is to move the idea of a directional universe from the realm of intriguing speculation into the domain of rigorous, testable science, where it must either stand up to the most precise observations we can make or be consigned to the history of fascinating but ultimately incorrect ideas. This collaborative, data-driven effort represents the very best of scientific exploration, a global endeavor to answer one of the most profound questions we can ask about the nature of reality itself. While the grand filaments of the cosmic web captivate with their dense splendor, it is actually the profound emptiness between them that might hold the most sensitive clues to the universe's true geometry. These are the cosmic voids, unimaginably vast regions of space that can span hundreds of millions of light years, yet contain almost nothing, just a few scattered, lonely galaxies adrift in a sea of near-total darkness. In the standard model of cosmology, these voids are expected to be roughly spherical. Gravity acts equally from all sides, pulling matter out of these regions and causing them to expand. But this expansion should have no preferred direction, resulting in voids that are, on average, shapeless and round. They are the great deserts of the cosmos, and their very emptiness makes them perfect, pristine laboratories. This is because, unlike dense galaxy clusters where complex gravitational interactions can scramble any subtle signals, the voids are simple. Their evolution is dominated by a single, clean process, the overall expansion of the universe. This makes them incredibly sensitive probes. If that background expansion has even a tiny preference for one direction, the voids would feel it first and most clearly. Imagine a collection of bubbles in a pot of gently simmering water. If the heat is perfectly even underneath, the bubbles will rise straight up, remaining roughly spherical. But if the heat is slightly stronger on one side of the pot, those bubbles will become stretched and elongated as they rise, their shapes betraying the unseen current beneath them. In exactly the same way, a universe expanding with a hidden directional preference would not create spherical voids. Instead, it would gently sculpt them, stretching these great cosmic emptinesses along the axis of its growth. Over billions of years, this subtle shearing force would leave a distinct signature, a population of voids that are not round but elliptical, and most importantly, all aligned in the same general direction, like countless seeds all pointing the same way. Astronomers are now using massive galaxy surveys to go looking for this very signature. By employing sophisticated algorithms to map the three-dimensional boundaries of thousands of these voids, they can statistically analyze their shapes. The initial results are tantalizing. Some studies analyzing data from the Sloan Digital Sky Survey have indeed found a faint but persistent signal that the largest voids are not perfectly spherical. They show a slight tendency toward being prolate or football-shaped, and there are hints that their orientations are not entirely random. While the statistical significance is still not strong enough to claim a discovery, and other effects like observational biases must be ruthlessly ruled out, these tentative alignments are precisely what an anisotropic model would predict. The emptiest places in the universe, once thought to be mere backdrops to the drama of galaxies, are now front and center in the quest to understand the fundamental nature of cosmic expansion, their profound silence potentially echoing the direction of a hidden dimension. To understand how a hidden direction in the cosmos could have shaped the very first structures, we need to journey back to a time before the first stars had even ignited, to an era known as the Cosmic Dark Ages. The universe was a vastly different place then, an expanding, cooling fog of neutral hydrogen and helium gas, utterly dark and silent. The only seeds for future growth were the tiny ripples in density, the microscopic quantum fluctuations from inflation that had been magnified to cosmic proportions. In a perfectly isotropic universe, these seeds were random, and the gravitational collapse that eventually turned them into the first stars and galaxies should have happened evenly, a stately and uniform process of structure formation beginning all across the cosmos at roughly the same time. Now introduce the possibility of a fundamental anisotropy, a universe that was ever so slightly stretched along a hidden axis even in its infancy. This subtle directional preference would have acted like a cosmic greenhouse, creating conditions that were not the same everywhere. Along the axis of preferential expansion, the dynamics of the primordial gas would have been uniquely different. The rate at which matter could flow and collapse under its own gravity could have been either enhanced or hindered by this background current. It's possible that along this special direction, the gravitational wells formed by those initial density fluctuations were just a little bit deeper, or the gas could cool and condense just a fraction more efficiently. This wouldn't have created galaxies out of nothing, but it could have given star formation a significant head start in certain regions of the sky. The consequence of this is staggering to consider. Instead of the first stars flickering on at random across the darkness, their ignition might have followed a pattern. We might find that the very earliest, most massive stars and the first protogalaxies formed preferentially along a vast, invisible corridor in space, a kind of cosmic fertile crescent where the conditions for birth were just right. The rest of the universe would have followed suit, but this first wave of structure, the pioneers of the cosmic dawn, could have carried an indelible imprint of the universe's underlying geometry. Their distribution across the sky wouldn't be random. It would show a faint statistical tendency to align, a whisper of order in the initial chaos of creation. This is not just theoretical speculation. It is a prediction that we can now test with our most powerful new eye on the early universe, the James Webb Space Telescope. Webb is fundamentally changing the game by peering back to the epoch of reionization, the period when the fierce ultraviolet light from those first stars and galaxies began to burn away the primordial fog. By cataloging the positions, ages, and types of these incredibly distant, high-redshift galaxies, astronomers can now create a detailed map of how structure formation began. The critical test will be to analyze this map for any sign of large-scale alignment. Do the very oldest galaxies we can find show any tendency to line up? Does the timeline of reionization itself seem to have progressed more rapidly along one particular axis of the sky? If such a pattern emerges from the data, it would be a monumental discovery, providing a direct link between the geometry of the universe's growth and the very dawn of light itself. It would mean that the hidden direction we've been searching for didn't just influence the universe's expansion. It also guided the birth of its first structures, writing its signature into the oldest chapters of cosmic history. Now, let's venture into one of the most profound and startling implications of a cosmos with a hidden direction. The very laws of physics themselves might not be constant. We take for granted that the universe operates on a fixed set of rules. The fine structure constant, which governs the strength of electromagnetic interactions, and the proton-to-electron mass ratio, which sets the scale of atoms, are believed to be immutable, their values the same in a distant galaxy as they are here in a lab on Earth. This uniformity is the bedrock of science. It allows us to confidently interpret the light from the farthest reaches of the cosmos, trusting that the atomic physics we understand here applies everywhere. But if the universe is fundamentally anisotropic, this bedrock begins to feel more like shifting sand. In such a model, the hidden dimension isn't just a direction for growth. It could be a gradient along which the very fundamentals of reality gently slope. The vacuum of space itself, the quantum foam from which particles and forces emerge, might not be perfectly uniform. Its properties could vary subtly depending on your orientation or location relative to this unseen axis. This means a fundamental constant like the fine structure constant might have one value for a galaxy aligned with the hidden dimension and a slightly different value for a galaxy oriented against it. The change would be incredibly slight, perhaps only a few parts in a million over vast cosmic distances, but even a variation that tiny would have earth-shattering consequences for the stability of matter and the very possibility of chemistry. To grasp the sheer magnitude of this idea, imagine a universe where the rules of the game change depending on where you're standing. The fine structure constant, often represented by the symbol alpha, is a magical number that determines how tightly electrons are bound to an atomic nucleus. If alpha were even a few % larger, atomic nuclei would struggle to hold onto their electrons, making the formation of stable atoms nearly impossible. Chemical bonds, the very things that allow for molecules like DNA and proteins to exist, would become feeble or impossible. Conversely, if it were smaller, electrons would orbit nuclei so tightly that complex chemical reactions might never occur. Life, as we understand it, is exquisitely tuned to the specific value of alpha we measure here. A proton is about 1,836 times heavier than an electron. This specific mass ratio is crucial for the stability of atoms and the formation of the elements in stars. Alter this ratio, and you alter nuclear fusion itself. Stars might burn their fuel too quickly or not at all, dramatically changing the life cycle of galaxies and the cosmic availability of the heavy elements necessary for planets and life. A universe where these constants vary is not just a slightly different version of our own. It is a cosmos that could be largely barren, filled with regions where physics simply doesn't allow for complexity to arise. For decades, astronomers have been conducting a grand cosmic experiment to test this very idea. They use the most powerful telescopes on Earth to study the light from incredibly distant quasars, the luminous cores of active galaxies billions of light years away. As this light travels across the universe, it passes through immense clouds of interstellar gas. Atoms within these clouds absorb specific wavelengths of light, leaving behind a unique fingerprint of dark lines in the quasar's spectrum. By analyzing the precise positions of these absorption lines, scientists can check if the atomic properties of that distant gas cloud are identical to those we measure in laboratories today. A shift in the lines would indicate a shift in the fundamental constants that govern those atoms. Some research teams have indeed reported tantalizing, controversial evidence of such a shift. They claim to see a very slight change in the value of the fine structure constant that seems to depend on the direction they look in the sky, as if there's a preferred axis across the cosmos along which the laws of physics gradually change. This potential discovery, often called the Australian dipole due to the team that first proposed it, remains hotly debated. Other groups using different data or methods have found no such variation. The scientific community is rightly cautious, demanding more data and independent confirmation, but the mere possibility is electrifying. If these observations were ever conclusively verified, it would be a discovery of unparalleled importance. It would do far more than just confirm that our universe has a preferred direction. It would forge a direct and undeniable link between the large-scale geometry of the cosmos and the small-scale laws of quantum physics. We would have to accept that the rules of the game are not written in a timeless, universal rulebook, but are instead woven into the fabric of spacetime itself, emerging from its structure and capable of changing with it. This would force a complete rewrite of modern physics, challenging both the standard model of particle physics and general relativity, and pushing us toward a truly unified theory where the cosmos and its constants are intimately and dynamically connected. We would be forced to confront the possibility that our local patch of the universe is not just a random location, but a very special one. A Goldilocks zone not only in space and time, but in the very laws of physics, a place where the constants are just right for us to exist and to look up and wonder why. This idea that the very fabric of reality might have a grain, a subtle directional preference, does far more than just add a new variable to our equations. It strikes at the heart of a philosophical foundation that has guided science for centuries. The Copernican principle, the profound and humbling realization that we do not occupy a privileged or central position in the cosmos, has been a cornerstone of modern thought. It taught us that the Earth is not the center of the solar system, the Sun is not the center of the galaxy, and our galaxy is just one among countless others in a vast, homogeneous expanse. This principle of mediocrity is the bedrock upon which we've built our understanding of the universe, allowing us to assume that the physical laws we discover here are universal, applying equally in every corner of spacetime. It's a democratic, egalitarian view of reality. But if the universe possesses a fundamental anisotropy, a preferred axis of growth, this entire world view begins to crumble. Location and orientation suddenly become critically important. A universe with a direction is a universe that is not the same everywhere. This doesn't mean we return to a pre-Copernican idea of being at the geometric center, but it introduces a new kind of specialness, not of place but of alignment. Our local region of the cosmos, with its specific orientation relative to this hidden axis, might enjoy a very particular set of physical conditions. Other regions tilted differently against this cosmic current could be fundamentally alien. The constants of nature, the strength of gravity, the speed of light, the mass of an electron, which we have always assumed to be immutable and universal, might instead be local bylaws, their values gently shifting along this hidden dimension. This possibility transforms the cosmos from a uniform arena into a structured, and perhaps even hierarchical, landscape. Consider the staggering implications for the possibility of life. We exist because the fundamental constants of our universe are exquisitely fine-tuned to allow for the formation of atoms, molecules, stars, and planets. If these constants were to vary even slightly, the delicate chain of events that leads from the Big Bang to biological complexity would be broken. In an anisotropic universe, this fine-tuning might not be a miraculous global property, but a local accident. We might find ourselves in a cosmic Goldilocks zone, not just in space and time, but in orientation, a placid backwater where the physics is just right, while other regions, oriented differently, are barren wastelands governed by different, perhaps more hostile, physical laws. This perspective doesn't make us central, but it does make us fortunate in a new and profound way. Our existence hinging on the specific way our three-dimensional slice is cut from a higher dimensional reality. This expands the concept of reality itself. If physical laws can vary, then other parts of the universe could be home to forms of matter, energy, and even life that are utterly unimaginable to us, based on chemistry and physics we can scarcely conceive. These wouldn't be separate universes in a multiverse, but distant provinces of our own cosmos, forever separated from us not by impossible distances alone, but by an insurmountable barrier of incompatible physics. The universe becomes a far richer and more mysterious place, a structured cosmos of immense diversity where the quest to understand our place is no longer about finding our spot on a map, but about understanding our alignment within a hidden geometry. This realization forces a profound shift from asking, where are we to a much deeper question. What are we in the context of a reality with dimensions and directions beyond our perception? For all its grand mysteries of dark energy and hidden dimensions, one of the most stubborn and precise problems in all of cosmology involves an element you can find in your cell phone battery: lithium. The story of the universe's first 3 minutes, known as Big Bang nucleosynthesis, is a spectacularly successful chapter in our cosmic history. The Standard Model predicts with incredible accuracy the amounts of the lightest elements, hydrogen, helium, and their isotopes forged in the incredible heat and density of the newborn cosmos. The calculated abundance of helium-4, for instance, matches what we observe in ancient gas clouds almost perfectly, but there is a glaring, persistent exception. When it comes to lithium-7, the predictions are all wrong. The equations say there should be about 3 times more lithium in the oldest stars than what we actually see when we point our spectrographs at them. This isn't a small margin of error. It's a factor of 3 discrepancy that has resisted explanation for decades, a nagging thorn in the side of an otherwise flawless theory. It's known simply as the Lithium Problem, and it hints that our understanding of the universe's first moments might be missing a crucial ingredient. This is where the concept of an anisotropic universe moves from the vast, abstract scales of galactic filaments and into the incredibly fine-grained realm of nuclear physics. The process of nucleosynthesis is a delicate dance of particles and energies, a race against time as the universe expands and cools, freezing the abundances of elements in place. The reaction rates that determine how much of each element is created are exquisitely sensitive to the conditions of the early cosmos: its density, its temperature, and critically, its rate of expansion. In our Standard Model, we assume that expansion was perfectly smooth and isotropic, the same in every direction. But what if it wasn't? If the infant universe was already exhibiting a tiny preference, a slight directional stretch, it would have fundamentally altered the environment in which these first elements were cooked. An anisotropic expansion during those first critical minutes would not have been a gentle, large-scale effect. It would have been a powerful, pervasive influence on the microcosm. Different expansion rates along different axes would change the cooling rate of the universe. A faster expansion along one dimension would have caused the primordial soup to thin out and cool more quickly than in an isotropic model. This change in the thermal timeline is everything for nuclear reactions. A faster cooling rate would have cut short the time available for certain nuclear processes to run to completion. Specifically, the reaction chain that ends with the production of lithium-7, primarily through the decay of beryllium-7, might have been truncated. With less time to operate, these reactions would have produced a smaller final yield of lithium, potentially bringing the theoretical predictions right in line with the frustratingly low amounts we actually observe out there in the cosmos. The sheer elegance of this solution is what makes it so compelling. It uses a single, coherent physical principle, a directional preference in the growth of space-time, to solve problems on vastly different scales. The same underlying mechanism that could explain the large-scale flow of galaxy clusters and the alignment of the cosmic web might also resolve a precise, decades-old puzzle about the abundance of a single element. This connects the impossibly large to the infinitesimally small in a way that few theories ever do. It suggests that the signature of a hidden dimension isn't just written in the distribution of galaxies. It might be etched into the very atoms that make up the stars themselves, a fossil from the first 3 minutes that has been waiting in plain sight all along. This demonstrates the profound power of questioning our most basic assumptions. The lithium problem has persisted for so long because cosmologists have primarily tried to solve it within the existing isotropic paradigm, tweaking nuclear reaction rates or proposing new particles. The idea of anisotropic expansion offers a solution from outside that box, showing that the answer might not lie in new particle physics, but in a new understanding of the spacetime stage upon which all physics plays out. It proves that truly comprehensive models have the power to illuminate multiple corners of reality simultaneously, providing a more unified and elegant picture of the cosmos from its very first moments to its present-day large-scale structure. To truly grasp how a universe with a preferred direction can be more than just a fascinating idea, we must dive into the rigorous mathematical language that makes it a credible scientific possibility. This language is provided by Bianchi Cosmologies, a sophisticated classification system for universes that are not perfectly smooth and symmetrical. Think of it this way: our standard model of the cosmos uses the Friedmann-Lemaitre-Robertson-Walker metric, which describes a universe that is essentially the same in every direction, like a perfectly risen loaf of bread where every raisin moves away from every other raisin at the same rate. It's a beautifully simple and powerful model, but it is just one specific solution to Einstein's complex equations of general relativity. The Bianchi classifications unlock a much wider and more exotic menagerie of possible universes. These are solutions to Einstein's equations that relax the strict assumption of perfect isotropy. Instead of a single, uniform expansion rate, Bianchi models allow the universe to behave differently along different axes. In one of these models, the universe could be expanding rapidly along an x-axis, more slowly along a y-axis, and perhaps even contracting along a z-axis. Beyond just different expansion rates, these models can incorporate other fascinating dynamics like rotation, where the entire cosmos has a slight spin, a concept that once unsettled Einstein, or shear, which is a kind of twisting distortion that can change the shape of objects in space over time. This isn't wild speculation. It's the direct result of applying the full power of Einstein's theory without imposing our aesthetic preference for symmetry. It reveals that the equations of gravity themselves do not demand a uniform cosmos. They permit a stunning variety of possible realities. This mathematical framework is absolutely essential because it turns a philosophical "what if" into a quantifiable, testable hypothesis. By cataloging all the possible types of anisotropic universes, theorists can create a precise playbook of their expected behaviors. How would the temperature variations in the cosmic microwave background look in a Bianchi-type Roman 7 universe versus a type Roman 9? How would galactic filaments align in a model with significant shear? These aren't vague guesses, they are specific predictions generated by solving these complex equations. This allows cosmologists to take real observational data, the precise map of the CMB from the Planck satellite, the three-dimensional distribution of galaxies from the Sloan Digital Sky Survey, and run statistical tests against the predictions of various Bianchi models. They can ask rigorously, does our universe show any faint but detectable signature that matches one of these anisotropic templates? This process provides a firm foundation, ensuring that the search for a cosmic direction is grounded in the solid rock of general relativity, not the shifting sands of pure imagination. This rigorous approach allows scientists to strictly constrain how much anisotropy our universe could possibly have. The incredible smoothness of the cosmic microwave background tells us that if our cosmos is anisotropic, it must be only very slightly so. The deviations from perfect symmetry are tiny, but the key question is whether they are zero. Bianchi cosmologies give us the tools to measure that, by seeing which models are completely ruled out by data and which remain even marginally possible. We are effectively taking the universe's temperature, checking it for any fever of asymmetry. The fact that some anisotropic models can still fit the data while also potentially explaining anomalies like the Hubble tension or certain CMB asymmetries is what keeps this field alive and exciting. It demonstrates that we are not just exploring mathematical curiosities, we are carefully probing the edges of our standard model, looking for the fingerprints of a more complex and perhaps more interesting reality. This unshakable forward march of time from a structured past to a disordered future is one of the most fundamental and puzzling features of our existence. We call this the arrow of time, and it is intimately tied to a concept in physics known as entropy. Entropy is essentially a measure of disorder, of randomness in a system. The second law of thermodynamics states that the total entropy of a closed system, like our universe, can never decrease over time. It always increases or at best stays the same. This is why ice melts in a warm room but never spontaneously refreezes, why a shattered glass doesn't leap back onto the table and reassemble itself. The universe is on a one-way trip from a state of low entropy, of high order, to a state of maximum entropy, of ultimate disorder and equilibrium. This relentless increase in entropy gives time its direction. It's the reason we remember the past but not the future, but this presents a profound mystery. Why was the entropy of the universe so incredibly low in the first place? The Big Bang appears to have been a state of exquisite order, a highly structured starting point that set this entire irreversible process in motion. Explaining this initial low entropy state is one of the biggest challenges in cosmology. Now, imagine introducing a new variable into this puzzle, a universe that is not expanding uniformly but has a preferred direction of growth. This anisotropic expansion could be the missing link that connects the large-scale geometry of the cosmos to the very local experience of time's arrow. If the hidden dimension is itself evolving, stretching and changing in a specific way, it could be acting as a kind of master clock or a conductor for the flow of entropy across the entire cosmos. The dynamics of this hidden dimension could have dictated the initial conditions of the universe, setting that crucial low entropy state at the Big Bang. Perhaps the process of this dimension beginning to expand, or its specific configuration, effectively wound up the cosmic clock, providing the necessary order to seed everything that followed. From that moment on, the continued evolution of this dimension, its own stretching and changing, could continually drive the increase of entropy in the visible dimensions we experience. In this view, the reason entropy always increases isn't just a statistical fluke. It's a direct consequence of the universe's underlying anisotropic geometry. The arrow of time isn't pointing in a direction within space. It might be pointing along the direction of the universe's hidden growth. Our local experience of time flowing from past to future could be a shadow, a projection into our three-dimensional world of a deeper evolution happening in a dimension we cannot perceive. This offers a breathtakingly elegant potential solution to one of physics' oldest and most difficult problems. It suggests that the nature of time itself might not be a primitive property of reality, but an emergent phenomenon that arises from the specific way our universe is structured and evolving. Understanding this connection would be a monumental step forward, finally weaving together the thermodynamic arrow of time with the gravitational dynamics of the cosmos. It would mean that the reason we perceive a past, present, and future is fundamentally linked to the fact that our universe is not a static, symmetrical stage, but a dynamic, growing entity with a hidden direction, forever moving toward a more disordered state, guided by the unseen geometry of its own higher dimensional nature. As we bring together the many strands of this investigation, a compelling and surprisingly cohesive picture begins to emerge from the cosmic tapestry. The journey started with a simple but profound question: could the universe be growing in a direction we cannot see? From that starting point, we have ventured through the mathematics of extra dimensions in string theory, analyzed the subtle fingerprints in the ancient light of the cosmic microwave background, and traced the potential influence of a hidden axis on the vast cosmic web of galaxies and voids. We have seen how this single, elegant idea could offer fresh perspectives on the most stubborn puzzles in modern cosmology, from the mysterious push of dark energy and the troubling Hubble tension to the curious case of the missing lithium. Each of these threads on its own might be dismissed as a curious anomaly or an interesting but far-fetched speculation. But when you begin to weave them together, they form a pattern that is far greater than the sum of its parts. This is the true power of the anisotropic cosmology framework. It is not merely a patch for one specific problem, but a potential master key capable of unlocking multiple doors simultaneously. What makes this synthesis so powerful is its ability to connect the unimaginably large with the infinitesimally small, the abstract with the observable. The theoretical possibility of unfurling extra dimensions provides a physical mechanism. The curious alignments in the CMB and the large-scale structure offer tantalizing, if still debated, observational hints. The potential to resolve the Hubble tension and the lithium problem shows how this idea could bring coherence to disconnected fields of study, and the profound philosophical implications challenging the Copernican principle and suggesting our physical laws might be local rather than universal force a complete reevaluation of our place in the cosmos. This isn't just a new model, it is a new way of seeing, a lens that reveals hidden connections between phenomena that once seemed entirely separate. It demonstrates that the most profound scientific advances often come not from adding more detail to an existing picture, but from stepping back and questioning the frame itself. Of course, this grand synthesis remains firmly in the realm of compelling possibility rather than proven fact. The evidence is suggestive, not conclusive. The anomalies could still be statistical flukes or artifacts of measurement. The true test lies ahead, with a new generation of telescopes and surveys that will map the universe with unprecedented precision, searching for the definitive signature of a preferred direction. Yet, even in its current speculative state, this line of inquiry is immensely valuable. It embodies the very spirit of scientific exploration, the courage to question deeply held assumptions, the creativity to develop new models, and the rigor to put those models to the test. It reminds us that our current understanding of the universe, however successful, is almost certainly incomplete. The cosmos has consistently proven to be stranger, more complex, and more wonderful than we ever imagined, and there is every reason to believe that trend will continue. This ongoing quest, driven by curiosity and a desire to understand our place in the grand scheme of existence, is what ultimately pushes the boundaries of knowledge and reveals a reality far richer than we could have ever dreamed. The possibility that the universe is growing in a direction we cannot see invites us to a state of profound humility and exhilarating curiosity. It challenges one of our most deeply held convictions, that the cosmos is an even, featureless expanse, and replaces it with a vision of a structured, dynamic reality where orientation and location might matter in ways we are only beginning to imagine. This isn't just a minor adjustment to a scientific model. It is a fundamental shift in perspective that echoes the great cosmological revolutions of the past. Just as Copernicus moved us from the center of the solar system and Hubble revealed an expanding universe, the discovery of a cosmic direction could redefine our understanding of physical law itself, suggesting that the constants we hold as universal might instead be local, and that our entire observable universe might be tilted against a hidden current we are only now learning to sense. This pursuit exemplifies the very best of the scientific spirit, The courage to question foundational assumptions, the creativity to develop new models, and the patience to test them against the hardest data we can gather. It is a journey that connects the furthest reaches of theoretical physics with the most precise astronomical observations, showing how abstract mathematics can make concrete predictions about the nature of reality. Whether the final answer confirms a directional universe or not, the investigation itself pushes our knowledge forward, refining our tools and sharpening our questions. Future missions, from the James Webb Space Telescope to the Euclid spacecraft and beyond, will provide unprecedented maps of the cosmos, offering new chances to detect the subtle signatures of anisotropy or to finally rule them out. This is how science progresses, not in a straight line, but through a process of bold speculation and rigorous testing, where even a negative result is a valuable step toward a deeper truth. As we continue to map the cosmos on its largest scales and peer back to its earliest moments, we may find that the hidden dimensions and preferred directions are not merely mathematical curiosities, but fundamental features of existence. This would mean that the universe is not just a vast collection of galaxies, but a structured entity with a geometry far richer and more complex than we ever dreamed. It would connect the quantum foam of spacetime's origin to the grand architecture of the cosmic web, offering a glimpse into a unified reality where the very large and the very small are woven together by the same underlying principles. Such a discovery would not be an end point, but a new beginning, opening doors to questions we have not yet even learned how to ask about the nature of dimensions, the variability of physical law, and our own place within this magnificent and hidden architecture. Thank you for joining this journey into the unknown. The next time you find yourself under a clear night sky, take a moment to really look at it. Remember that the countless points of light are not just distant suns, but markers in a vast, three-dimensional map that may itself be oriented within a higher dimensional reality. The true nature of the cosmos is likely far stranger and more wonderful than we can currently perceive, and every new discovery reminds us that the greatest adventure lies not in the answers we possess, but in the mysteries that remain. Keep looking up and keep wondering what lies just beyond the edge of our perception.